Okay, so now we have another element to discuss, this heat and work type thing, okay? Alright, so now we know how energy is transferred in and out of a system in terms of Q and W. Well, what the heck do they mean? What is heat and what is work? What do we mean by this? Well, work is a very subjective thing, and we as humans, we've described what work means for us. Work is defined as use a measurement of useful energy. Okay? What do I mean by useful energy? Okay. I can have, for example, a piston. Okay? And I have a gas mixture here. And I will let this react. As it reacts, it will move the piston up. And move that up from an initial location here. Okay, it changed location as the gas mixture expanded. Okay, if I hook up a some sort of rod to it that's got blades or something, I can have the expansion do something for me. Maybe I'm sitting right here and it's a fan, and I'm enjoying the cool air that it's making for me. Or maybe I'm making something a little more useful in that it's an engine and it can run a car or something like that. Whatever it is, it's something that's very subjective. It's what we define as something that we want. It's our ability to take this energy thing that just exists in the universe and for us to use it for our purposes, to make our lives better. And depending on the application, we define work differently. Okay, so that's what work means. And again, if the work is positive, that means the system is doing the work, which is usually what I want. So I want my car to do work, so I want the work to be positive. I don't want to have to do work on my car. I don't want to have to push my car up a hill. I want the car to push me up the hill. So the car itself, which is my system, I want it to have positive work, and I don't want to put work into it. Of course, whenever I go to the gas pump, I have to put work into it, and I pay for it. Okay, and so that's the idea of work. And heat is just basically a transfer of energy that, for the most part, but not always, has some sort of an implication of a change in temperature. We usually measure it with temperature, but not necessarily. But heat is basically what remains out of the energy. Okay? So, after we discuss the second law of thermodynamics, we will have a much better understanding of the interplay between heat and work. Right now, I am holding back a lot because we don't have the tools yet to discuss it, and I don't want to jump right into that. So the first law just defines, the first law of thermodynamics tells you that something exists, there is energy, that it does stuff, okay? That it has to be conserved, but it doesn't give you much by way of why. The second law of thermodynamics, when we get to it, will explain the why behind the whole thing. This is more like of a what, where, when, and how. Second law of thermodynamics comes in and just explains, well, this is why it's happening. And this is the maximum ability, and this is how I'm going to be able to push it to the limits of it. So we're not going to discuss that why yet, but I will give you enough meat to understand all the nitty-gritty anyway, just I will hold back with some ideas. Okay, so now we talked about work and heat, and we will talk in a few minutes how to measure these things. So I mentioned that no matter what it is that you're doing, no matter what type of energy that you have, you can put it under an energy of movement, or you can put it under an energy being stored. Okay, and if something that's stored can do work for me, I could do stuff with it. If something is moving, well, something moving could do work for me as well. Or I can move something and then I'll store energy and use it later. That's sort of the interplay here. What I didn't mention is a very special type of kinetic and potential energy, and one that we cannot really control as well as we'd like. So consider this. Suppose I have a cup of water. Okay? And what I'm going to do is I'm going to put it maybe in some sort of styrofoam container. So I have water here. And I'm going to put it in some sort of insulation, some sort of styrofoam component that will allow me to basically say that this is an isolated system. And so if I just left it like this, as we discussed before, the whole idea of energy, this is isolated, meaning that this insulation won't allow heat to escape or enter. Okay, so in an ideal scenario, I mean, no matter what you do, you can perfectly insulate something. But suppose you did. So now the amount of energy that's in it is stuck there. Okay, it can't leak, can't enter, it's not going to be destroyed, not going to open it and it will have disappeared. It's there. Okay? And so the idea was, behind this experiment that was done in the 1840s, was to try to limit heat from leaving. Okay, because the only way for me to get energy into the system or out of the system is through heat and work. Okay, so what was done, okay, was two tiny holes were poked. Okay, so approximately insulated. Okay, so imagine Q is approximately 0. And then what was done is a thermometer was stuck in there to measure the temperature. Okay, so a thermometer, maybe it's got some sort of substance, maybe like mercury or something like that, and some readout. So the person was able to read it out. And on the other end of it, this guy actually put several different things. I don't know if we'll be able to see this different color. It's purple. Yeah, you can see it. Sorry. So the first thing that he did was put a paddle in it. Okay? And what was done here is that this paddle did some work. Okay, it did some work onto this water. And he didn't allow, by he, I'm really obfuscating the whole thing, Joule, the namesake of the unit Joule, a physicist from the 1800s, put in a paddle into this thing and spun it. So he provided work into this system, and he wanted to know whether the energy will change. And he recorded it using the temperature. Okay? So then, since the energy has to be kinetic and potential, he surmised that if I did this, I will be able to provide some heat, some energy into this. Heat won't have escaped. The only way for me to change the energy is through this work. So I'm in effect storing some sort of energy. So he was able to do this, and he put some sort of work into it. And with this work, he was able to raise the temperature of this water by a degree. So he measured it all in the customer unit. So he did 1 degree Fahrenheit, and he put, I forget how much, 700 and something foot-pounds into this, and he was able to raise it and see that there was actual change. So in this system, what he did, he said that delta E was going to be negative W. And he basically said this is going to be a kinetic and a potential energy. So when he let go of this ability to do work, well, what moved? What work was done? Where was it stored? Okay, so how did it happen? That was kind of his idea. Like, how can I quantify this? Because when I'm talking about balls rolling down, or if I'm talking about some electric circuit, I could understand that electrons are moving. I can understand that the ball's rolling downhill. I can understand when I'm burning calories when I'm eating. What the heck is happening here that is storing or doing work? And so the idea here that he's derived is that there is a macroscopic kinetic energy, a macroscopic potential energy, and then there is a microscopic kinetic and potential energy. And that's kind of what he derived here, and I'll show you in a second. But the idea is, I can break this down and say I have delta KE on the macro plus delta PE on the macro plus delta KE plus delta PE. Both of these things will be micro level on the atomic level. What he did, he called this thing a quantity, and he called this the internal energy. And he just experimented and showed that there is this thing called internal energy. and he called this thing delta U. And that's kind of what that means. Well, not that was that. Literally what it means is that the ability to store chemical ability for the atoms or molecules to do something and then later on move. Okay? So if he provided all this work into this system, right? And then he wanted to melt something. A system that he put more work into could melt the thing faster and more efficiently than a system that he didn't, right? So in a sense, if I put a cube of ice into a cup of water that's 1 degree Celsius, it will melt, it will take a while. If I put a cube of ice into a cup of water that's 99 degrees Celsius, it will melt fairly quickly. And so the idea is he put work into it, and the work that he put into it was translated into an internal energy, and this is basically a macroscopic energy. Okay? So what people often do is they augment the first law of thermodynamics to include that. So they basically write delta U is delta E is delta U plus the macroscopic, and they don't even write macroscopic, but it is understood that that's what they mean. That this is macroscopic, like for something that's like an object, like a ball or an elephant or anything that's visible to us. And the only way for us to kind of move them up or down, and move this up or down, is through heat and work. Okay? And we will discuss enthalpy in a bit, but enthalpy is related to this delta U. It's basically a dumping function. We will get to that in a bit, and I'll do a separate video where I just explain what delta H, which is enthalpy, is. And that one will just focus on why I call it a dump function. We dump all the stuff we don't want and put it into it. But it is going to act very similarly to delta U. So watch for that as another video. Okay, so this I won't focus on much. This I will. Let's discuss all these types of work.